Hello, my name is Muhammad Syamil Aizat. Today we present a case study on thermal pollution near a coastal power plant focusing on Kapar Power Station in Selangor, Malaysia. Thermal pollution occurs when seawater used for cooling in power plants absorb waste heat and is discharged back into a marine environmental at elevated temperatures. This process alters natural temperature regimes and cause localized warming of coastal waters in tropical regions where marine ecosystem already experience high baseline temperature. Even small increase of 3 to 6 degrees Celsius can significantly affect water quality and marine organism. For the source of pollution and site background, the source of thermal pollution in this study is once through seawater cooling system used at Kapar Power Station. Seawater absorbs heat from the power generation process and is discharged directly into the seawater without further cooling, forming thermal plants near the discharge outlet. Kapar Power Station is located on the west coast of Peninsular Malaysia and has been operating for many years. The plant is situated nearly densely populated coastal and fishing communities, increase the environmental relevance of the thermal discharge in this area. For the problem statement and current finding, the first is despite existing study, the spatial extent and persistence of thermal pollution near Kapar Power Station are not fully characterized. Many studies rely on short-term monitoring and do not adequately capture thermal plant behavior under very tidal condition. Current monitoring indicates that seawater temperatures near the discharge outlet increased by approximately 3.6 to 3.8 to 4.5 degrees Celsius above ambient levels. These elevated temperatures persist during low tidal mixing period and can extend up to 1 to 1.5 kilometers from the outlet, suggesting continuous rather than temporary thermal impact. For the next part of review of thermal pollution mechanism. Thermal pollution at Kapar Power Station is driven by it once through cooling system. Large volume of seawater are withdrawn with nearby coastal water and circulate through condenser, where they absorb excess heat from the steam used in electricity generation. After this process, the heat seawater is discharged directly back into the marine environment. The discharged water being several degrees warmer than the surrounding seawaters form a thermal plants near the outfall. The highest temperature occurs in the near field zone, while temperature gradually decrease with a distance offshore, and the size of intensity of the thermal plant depend on the tidal mixing, coastal circulation, and shallow water depth. During periods of a weak hydrodynamic circulation, particularly of low tide, the thermal plant remains concentrated near the coast, enhancing thermal persistence. Elevated seawater temperature also reduce dissolved oxygen levels and disrupt natural temperature stratification. And in tropical coastal environment like Kapar, where background temperature are already high, in this additional thermal load significantly increase vulnerability to thermal stress. For the next, as you guys can see, the table 1, regional comparison. Table 1 compare ambient seawater temperature and temperature elevation near discharge outlet of selected Asian coastal power plants. Kapar power plants record a temperature increase of approximately 3.8 to 4.5 degrees Celsius, which is comparable to other plants in the region, such as Manjung, Vung Ang, and Suralaya. This indicates that thermal pollution at Kappa follows a regional pattern associated with one true cooling system. However, the close proximity of the Kappa to populated coastal area highlight the need for site-specific management and mitigation.
Thank you, Shamel. My name is Muhammad Adam Darus. As we established, the long-term discharge at Kappa increased seawater temperature by 3.8 to 4.5 degrees Celsius above ambient. What's particularly concerning is that this thermal effect extends beyond the immediate outlet area during the certain tidal condition, creating a persistent thermal pollution zone affecting much larger area than initially anticipated. This effect the impact span all levels of marine ecosystem. Let me walk you through each group. Starting with plankton, these microscopic organisms from the base of the marine food web and are highly sensitive to temperature changes. Elevated temperatures promote thermophilic species while reducing overall biodiversity, affecting primary productions and nutrient cycling throughout the ecosystem. Next is benthic organisms living on the seafloor have a limited mobility, making them especially vulnerable to prolonged thermal exposure. The combination of high temperature and hypoxia accelerates organic matter degradation, fundamentally changing the seafloor environment. For shallow water habitats like coral and seagrass beds experience thermal stress that compromise their biological function and reduce their capacity to recover from other disturbance. Mobile fish species actively avoid warm waters, reducing fish availability, aligning with a local fishermen reports of declining catches. These ecological impacts translate directly into socio-economic consequences. Reduced fish stocks impact small-scale fishers' income. Poor water quality discourage coastal recreation. There's loss of tourism potential and dismiss a quality of life. Thermal pollution affect environmental, social, and economic dimensions simultaneously. It's not just an ecological problem; it's a community problem. Now, building on these impacts, I will now walk you through proposed mitigation and management strategies. Managing thermal pollution requires a holistic solution spanning engineering, operations, and environmental management. For engineering solution, the most direct approach is redesign cooling system, transition from once through to closed loop or hybrid cooling technologies significantly reduce discharge volume and temperature. For existing system, multi-port diffuser or submerged outfalls improve mixing and dilution, reducing temperature spikes near the surface where organisms are the most vulnerable. Next is operational managing and monitoring. Operational strategies can be implemented quickly by controlling timing and flow rate of discharge, particularly during low tide. We prevent thermal accumulation, implementing temperature limit based on ecological tolerance threshold directly reduce the biological stress. Continuous monitoring of temperature, dissolved oxygen, and biological indicators enables early detection and proactive management adjustment. Next is ecosystem-based approach. We should establish thermal buffer zone around sensitive habitats such as coral reef, seagrass bed, and aquaculture site. Restoration effort can be rebuilt resilience in degraded areas, critically engaging local stakeholders, especially fishing communities, improve compliance and balance environmental protection and socio-economic needs. This case study demonstrates that the thermal discharge create a localized yet persistent disturbance. Temperatures increase approximately 6 degrees Celsius above ambient, extending hundreds of meters from the outlet. Impact span all trophic levels from plankton through benthos to fish. Society organisms are most vulnerable due to prolonged exposure, while mobile species must relocate. This effect threatens biodiversity, habitat stability, ecosystem services, and local economies. Based on the findings, our recommendations are organized by stakeholders. Power plants should adopt improved cooling technologies and discharge management system. This is essential for sustainable operation. Regulatory bodies must establish enforceable temperature limits based on ecological threshold with mandatory monitoring programs. Next is future research needs investment in long-term ecological monitoring and develop numerical models to predict thermal plumb dynamics under varying conditions. In conclusion, mitigating coastal thermal pollution requires a coordinated action across engineering, regulatory, and ecological domains. Only through improved cooling system, strictened standards, and active monitoring and stakeholder collaboration can we reconcile industrial energy needs with marine ecosystem preservation. The challenge is clear. We must meet growing energy demands while protecting the environment that sustain ecological health and human well-being. The strategy outline provide practical roadmap from advancing this balance through commitment, coordination, continued vigilance. That's all from us. Thank you for your attention.